In progress. Hi, on just on. Only participant only. We'll be continuing the previous presentation now. So basically, I just on the other day wanted to add a little note on the stretch reflex because the major part of the muscle is also something called the muscle spindle, the intrafusal fibers. All these while we've been talking about the extrafusal fibers supplied by the alpha motor neuron, which gives its contraction. Now we'll be talking a little bit more on what intrafusal fibers is. It's how many are there, and then its sensory and motor innervation, its function and things like that, its higher control, where its control comes from, and then its use as such. So what is a monosynaptic stretch reflex? As we all know, contraction of a skeletal muscle in response to stretch is called a stretch reflex. It's all the jerks, the knee jerk, the ankle jerk that we do, that lies at the level of that spinal cord level, is is a good example of a stretch reflex. So what is the stimulus here? A stretch of the muscle is the stimulus. Now, what is the receptor? What senses this stretch? So the thing that senses the stretch is the muscle spindle. What is the response? Now, this gives out a signal to the spinal cord, and from the spinal cord, the specific neuron which supplies that muscle starts contracting. The response is the contraction of the muscle. Now, what is a muscle spindle? What is the structure? So it is a macroscopic structure, 4 mm spindle shape, as the name says, present within the muscle. So all these are present, they lie parallel to the extrafusal muscle fibers. And the number depends on the action of that specific area. Like for example, our hand, which is responsible for finer motor, the number of spindles will be more. That is, they say it's 150 per 5 gram. Whereas muscles which have a gross action, not finer motor, there are just 5 muscle spindles per 5 gram. That is the difference. For finer motor, you have more muscle spindle. Now, these are the intrafusal fibers that lie within the extrafusal fibers, muscle fibers. These extrafusal muscle fibers are nothing but the regular contractile units that we just spoke about in the last class. Now, the size, they are really small, 6 to 30 micrometer in diameter. How many are there? 2 to 12 muscle fibers. They're enclosed in the capsule. They lie parallel to the rest of the muscle, though the ends of the intrafusal fibers, they lie parallel, and ends are attached to the tendons, which then join with the extrafusal fibers. Now, they don't have much contractile activity. So there is a center and there is the end. So the only contractile part of this structure are the ends. And there are 2 types of intrafusal fibers. One is your nuclear bag fibers, and the other one is your nuclear chain fibers. So the nuclear bag fibers are nothing but they appear like a bag with multiple nuclei in the center. Whereas nuclear chain, as the name suggests, they appear like a chain, and the nuclei are arranged in the form of a chain. Now, how this appears, you have nuclear bag fibers. These nuclear chain fibers attach to the sides of the nuclear bag fibers. So these are the two important types. And like I told you, the nuclear bag, as the name suggests, all the nuclei are arranged in the form of a bag. Whereas nuclear chain, they're arranged in the form of a chain on two sides, and they attach to the nuclear bag fibers. Now coming to the innervation, this is the important part. So the sensory innervation, the afferent will be our 1A. So the three important afferents that we'll be talking about. One is the 1A, the second is 1B, the third is 2. So here, what is the afferent fibers that come into play are 1A fibers. They go, they connect like a spiral around the nuclear bag and the nuclear chain fibers. Otherwise, they are also called annulospiral endings. The primary endings are otherwise called annulospiral endings. So 1A afferent fibers around the nuclear bag and nuclear chain fibers, they wind around. Now, these what is the function of each of these fibers? Now, so for example, if I tell you what is the stimulus to 1A to be stimulated, that is a stretch of a muscle. So when the muscle is stretching, it's stretching. So there is a process, that is the dynamic event happening, and at the end of the stretch, at the end of the stretch, there is sustained stretch. So you keep pulling. So the dynamic response is when these sensory afferent fibers are stimulated when the muscle is getting stretched. But static response is when there is an afferent release, when there is sustained stretch. That will be a static response. So this dynamic response, the afferents that are basically in play are the afferents from the back fibers. So the afferents responsible for to detect the velocity at which it's getting stretched are your 1A fibers coming from the back fibers. But now the muscles completely stretched. There is a sustained stretch. What are the afferents getting activated? The nuclear chain fibers 1A endings get activated. Now this is responsible for to detect the length of the muscle. Whereas this back fibers are responsible for detecting the velocity at which the muscle is getting stretched. So that's how. So then the 1A fibers go to the spinal cord, and from the spinal cord, the alpha motor neuron, which supplies that specific muscle, comes into play, and the extrafusal fiber gets contracted. So when you're stretching, so it gives out a signal to not stretch too much, and the alpha motor neuron comes and contracts the muscle, and that shortens the muscle so that there's not too much stretch and the muscle does not tear. So then you have another insignificant afferent, that is your secondary or flower spray endings. These are the group 2 afferent fibers which go, and this is present only in the ends of the nuclear chain. So your nuclear bag as afferents, which is your 1A, and then your nuclear chain, you have 1A with spirals, otherwise called annulospiral, and then you have the flower spray endings. So in the end, the nuclear chain also has group 2 afferent fibers going to the spinal cord. But the end of the day, the end result is going to the spinal cord, coming back as alpha motor neuron and contracting the muscle within which these muscle spindles are present. That is a sensory supply. Now coming to the motor supply. So the motor supply is central. When I say motor supply, this is not the alpha motor neuron that I spoke about. This is direct supply from the centers of the brain. So you have beta afferents and you have gamma afferents. Those were the alpha, which the afferents went and stimulated. Now we have beta and gamma, which actually supply the motor units of the intrafusal. I already spoke about that there is not much contractile units in the intrafusal fibers. So what happens is beta afferents, they supply both extrafusal and intrafusal fibers, and they have low threshold to excitation. But whereas gamma afferents, otherwise called fusiform fibers, which primarily supply only the intrafusal fibers, it is not easy to stimulate them. Their threshold is quite high. There are two efferents here. One is your G1, gamma 1, and the other one is your gamma 2. Gamma 1 is the one which supply the nuclear bag. Gamma 2 supplies a nuclear chain. So what is the point of this gamma? It increases the sensitivity of the nuclear bag and nuclear chain fibers to stretch. So for example, the gamma 1 fibers are getting stimulated from the center. The sensitivity of the nuclear bag fibers are increased. Now there is a stretch of the muscle happening. Because the sensitivity is increased, it detects it. The nuclear bag detects it, the process of stretch that's happening. Now this stimulates the 1A afferent, goes to the spinal cord, come back to the alpha motor neuron, contracts the muscle. Now G2, gamma 2, again, they supply nuclear chain. They increase the sensitivity of the nuclear chain, so that the length of the muscle and the sensitivity to sustain stretch is detected. That's why they're also called dynamic gamma afferents and otherwise called static gamma afferents. So there are two mechanisms by which they act. One is called the lens servo mechanism. The other one is your follow-up servo mechanism. There's something, this lens servo and follow-up servo. Lens servo is to detect the movements of the muscle when the muscle is in movement. When the body is moving, it detects it. Whereas the follow-up servo is regulation of posture, static. That's the difference, how it acts. So here when the muscle is getting stretched, your muscle spindle is also getting stretched. But there are also centers, the central influence here. So the central influence is there is co-activation when you want to move. There is a central activation that you have to move. So there is an alpha and there is a gamma. Both get co-activated. So at this point of time, your extrafusal and your intrafusal fibers contract at the same time. But see, the whole point of intrafusal fibers is to detect it and contract the extrafusal. But both are getting activated here. So the point of gamma here is if there is an increased length or a decreased length, gamma is going to detect that. The change, if there is not appropriate extrafusal fiber response, this intrafusal fiber is going to detect it and correct it when in motion. So you don't, it is responsible for precision of contraction of the muscle. But when for regulation of posture, there is something again called alpha gamma linkage. So when the alpha is getting contracted, how is the gamma going to get contracted? So only when there is stretch, the intrafusal fiber detects it and the gamma gets activated. But here, if the muscle is getting contracted, there's not going to be intrafusal fiber activation at all. So the center sends gamma efferent discharges to increase the sensitivity. The whole point of this is, so at all points of time, there should be extrafusal fiber contraction. Even though it's contracting, there is a separate innervation to the gamma efferent leading to intrafusal fiber contraction. Now, since intrafusal fiber is getting contracted, there is constant, at the spinal level also, constant stimulation of the muscle to contract, and which helps us stay erect and maintain the posture. So the higher control, I spoke about the gamma efferent. Gamma efferent is primarily higher control. There are many centers here, but there are only few activatory centers. There is only one activatory center, that is the facilitatory reticular formation. This increases the gamma discharge and the reflexes are hyperactive in this case. So there is a constant spontaneous discharge happening. There are many inhibitory centers, but this is the prime one. This is the only one which is an activatory center. Then we have the vestibular nuclei, which acts on the alpha motor, does not act on the gamma motor. This directly causes extrafusal fiber contraction, whereas this is responsible for spontaneous gamma discharge. Now, what are the inhibitory centers? The primary inhibitory centers which go out are your inhibitory reticular formation. Now, this does not have spontaneous discharge like the facilitatory one. This acts only when it's getting stimulated by other centers. Like, for example, you have your motor cortex, we have basal ganglia, we have cerebellum, other centers which influence the gamma efferent discharge. The motor cortex and cerebellum both act, they reduce the gamma discharge. How do they reduce the gamma efferent discharge? By activating the inhibitory reticular formation. Hence reducing the gamma efferent discharge. Now, how does the basal ganglia act? It is also responsible for reducing your gamma efferent discharge, but how does it act? It either activates the motor cortex or it directly connects with the inhibitory reticular formation. So at the end of the day, all of this end up in inhibitory reticular formation, causing reduced gamma discharge. Now, a little bit on the muscle tone. The tension, so there is a continuous synchronous, asynchronous gamma discharge happening. This is that minimal tension that we develop when we stretch a muscle. That is caused by this. It's the resting tone of the muscle. The tension in the resting muscle due to low frequency and asynchronous gamma discharge motor neurons produces resistance of the muscle to stretch, passive stretch. Now, it's otherwise called the state of partial tetanus, and they are basically out of phase contraction. It's not like producing, it does not reach a threshold which causes significant contraction of the extrafusal fibers. Now, basis of the muscle tone, we all know if the tone is less, it is called hypotonic. If the tone is more, it's called hypertonic. Why I added this is, what are the possible regions in this pathway that we just spoke about where all if the pathology is pathology causing hypotonia, the lesion is where all. That's what I wanted to emphasize. So one, if the local arc is destroyed, then you have hypotonia. Then, or if the centers which are responsible for stimulation, like the facilitatory area, if that gets destroyed, it is then it causes hypotonia. Or in sleep, there is hypotonia, and certain drugs like barbiturates can cause hypotonia. Or if the centers in the brain which are inhibitory get stimulated, that also causes hypotonia. Now, how about hypertonic or spastic? Just the opposite. If the facilitatory areas are stimulated, that causes hypertonia. If the inhibitory centers are destroyed, that causes hypertonia. Any factor that increases gamma discharge causes hypertonia. Now, coming to the last part. So we have something, how now there is constant stretch of the muscle. I told you that the muscle keeps getting stretched. At one point, if you stretch it, it's going to tear. We have a protective mechanism which is going to stop that also. That is, there are two mechanisms by which there is inhibition of stretch reflexes. One is called the reciprocal inhibition. This is the basic pathway, the stretch reflex pathway. There is a stretch, the one A gets stimulated, it goes to the spinal cord, then the alpha motor neuron gets stimulated, contracts the muscle fiber, the extrafusal fibers, from which 1A gets out. But not only that, from that same efferent state, there is another branch which goes to the antagonistic muscle to relax it. So that the agonistic muscle can contract. That is called reciprocal innervation. So there is stretch reflex, afferents from the muscle spindles, alpha motor neurons, and muscle contraction. Impulses from the contracting muscle causes inhibition of the antagonistic muscle. This is called reciprocal innervation. This is a bisynaptic, like a bisynaptic transmission here. And this is the example of a postsynaptic inhibition. Ensures that the agonist muscle movement is not obstructed by the antagonist. This is one method in which the stretch reflex is inhibited. Because not only is it contracting the agonistic muscle, and this agonistic muscle contraction, there are fibers which come out which inhibit the antagonistic muscle. Two synapses, agonist and one to the antagonist.
Example of postsynaptic inhibition.
So, postsynaptic inhibition is the contraction, the activation of one muscle is inhibiting the action of another muscle, agonistic muscle. Now this is the inverse stretch reflex is the one which explains the mechanism of a Golgi tendon body. The organ here at play is a Golgi tendon body, which is present at the junction of the muscle and the tendon. So the whole point of this is, like I told you, if you keep stretching the muscle, it's going to tear. So at a point of stretch, extreme stretch, these Golgi tendon body gets activated. It goes to the spinal cord, sends out an inhibitory. So the afferents that go here, not 1A, not 2, it is 1B. These 1B afferents go to the spinal cord and sends out an inhibitory postsynaptic potential. So that causes relaxation of the muscle from which this afferents go. Like if you understand, I'll show it to you. So harder the muscle stretch, harder the muscle contraction. That is, the gamma efferent discharge is proportionate to the amount of stretch that's happening in the muscle. Only up to a certain point. Further increase in stretch, halting and contraction happens, and there is muscle relaxation. The organ that is responsible here is your Golgi tendon organ. These are the receptors that get activated at points of extreme stretch. This is otherwise called the autogenic inhibition or the inverse stretch reflex. Like with stretch, if there is relaxation, it is inverse stretch reflex.
So why is this not called a postsynaptic inhibition?
This is not a postsynaptic inhibition, and this is the only synapse. I'll show you, ma'am. This directly acts at the level of spinal cord. For example, there is a stretch. The 1B afferent goes to the spinal cord. Then there is an inhibitory. This is also postsynaptic. After the synapse happens here, there is an inhibitory postsynaptic action, postsynaptic inhibition. And there is an inhibitory interneuron here, which goes and it inhibits the alpha motor neuron, which supplies the muscle, from which these 1B fibers come from. For example, Golgi tendon organ gets stimulated, 1B fibers are activated. At the spinal cord, inhibitory interneurons get activated, causing an inhibitory postsynaptic potential. The motor neurons that supply the muscle of the origin of afferent, that is origin of 1B, there is inhibition of that. There is relaxation of the muscle. And there is an excitatory connection with the antagonistic muscle. So this is also bisynaptic actually. This is also bisynaptic and this is also inhibitory postsynaptic. The whole point of this is it's a protective reflex to avoid tearing of the muscle, and it regulates the tension during muscle activity. If the tension exceeds a point, it is going to inhibit itself, causing autogenic inhibition. That's it. Thank you.
You should have put some pictures of
I wanted to remember, this was like an additional note to the other presentation. That's why.
So in the muscle anatomy, you did not talk about the proteins.
Actin, contractile units.
Other proteins that are actually clinically important.
The desmin and all, actinin.
These are important.
This is my second presentation, sir. So I spoke about the smooth muscle and skeletal muscle anatomy, mechanism, how it contracts. Any doubts, sir? Manjunath, sir?
No, nothing. It was a good presentation. So you completed the topic, no?
Yes, sir. Yes, I completed the topic.
Okay, fine. Good. Nice presentation.
Thank you, sir. Thank you. Sonali, ma'am, any doubts, ma'am?
No, I don't have anything.
Okay, ma'am. Thank you.